Let us start this lecture, a thought process from Rudolf Clausius. He says heat can never pass from a colder to a warmer body without some other change connected herewith occurring at the same time. And of course, that we have seen as a part of what we call Clausius statement. It is impossible to transfer the heat from the cold region to the hot region without any external aid. We have basically discussed about various aspects of second law of thermodynamics, including Kelvin Planck statement, Clausius statement, and then we moved into the Carnot cycle analysis, and we also found out that the thermal efficiency of a Carnot engine is equal to 1 minus TL divided by TH, and which will give the maximum efficiency whenever an engine is operated between a thermal reservoir and a source and a sink. So, we looked at basically two corollaries, that is Carnot corollary 1 and Carnot corollary 2, and we will be now taking up an example to see how you can apply the Carnot corollary and solve a problem. So, let us take an example. So, this example generally it is related to claim being made by an inventor, and which is a things one has to clarify and one has to invoke the second law of thermodynamics. The example is like this: that an inventor claims to have designed and developed a new heat engine that can produce 45 kilowatt of power by absorbing 52 kilowatt of heat from a thermal reservoir at 700 Kelvin while rejecting heat to the sink at 300 Kelvin. Is it true or false? That you need to find it out. If you look at this problem, the question arises whether first law of thermodynamics being satisfied or not, right, and then we need to look at also the whether the second law of thermodynamics being satisfied or not. If you look at, like, it is basically what you call absorbing 52 kilowatt of power from a source, from a thermal reservoir at 700 Kelvin, and it produces 45 kilowatt of power. That means it is whatever the heat being absorbed is some portion is going to sink and 45 kilowatt of the power is being produced, and sink is at 300 Kelvin. That means it looks to be, it may be true. Let us look at whether it is true or not. So, for that what we will have to, we will have to find out the thermal efficiency. Thermal efficiency nothing but W dot by Q dot, and the work produced by this heat engine is 45 and heat absorbed from the source is 52. The efficiency is 86.5%, quite a bit. And now what you will have to do, you will have to basically invoke the Carnot corollary 2, which says no heat engine can be more efficient than a reversible engine operating between two thermal reservoirs, right. Suppose this engine, and then this is the actual engine whose efficiency 86.5, and if you say that Carnot heat engine is being operated between the temperature 700 Kelvin, that is the source, and the sink is 300 Kelvin, then what would be the efficiency? Efficiency would be equal to 1 minus TL by TH, and the TL is 300 Kelvin, right, and the TH, the temperature of the source, is 700 Kelvin, and you are getting the efficiency of 57.1%. That means a reversible engine is giving 57.1%, and the inventor is claiming his efficiency to be 86.5. Therefore, it is not really possible, right? And hence the claim of this inventor is false. So, by the using a very simple way, one can really find out whether it is true or not. So, let us now see how we can apply thermodynamics, apply the second law of thermodynamics for a temperature scale, which we have already discussed earlier. Let us devise a temperature scale which won't be dependent on the properties of the substance, that we have already defined as a thermodynamic temperature scale. If you recall, that is the thermodynamic temperature scale, which won't be dependent on the properties of the substance, like what we use. Let us say in a mercury and glass thermometer. So, if you look at the temperature, what it will measure, it will be dependent on the expansion of the what we call mercury. But if I use alcohol, then that expansion will be different. So, it will be dependent on the what we call substance, the thermometric fluid rather. But however, we need to devise a temperature scale which will be not dependent on the properties of substance. So, why is it required? We know, because we have already know that whenever this mercury glass and alcohol glass thermometer will be used, even though it will be calibrated at the ice point and boiling point, but however, it will give you different what you call temperature at other points. You may calibrate at the same ice point and boiling point and assign those values, but however, if you go deviate from this ice point and boiling point, it may give you different what you call values. For example, like mercury in glass thermometer will give you 50.12 degrees Celsius, whereas the alcohol in glass thermometer will give you 50.45 degrees Celsius. Of course, you may say, look, it is not much, but in accuracy wise it is not good. So, therefore, it indicates that the what you call this temperature scale is basically dependent on the properties of the thermometric fluid, right, because mercury and alcohol are two different and their properties are different, therefore. So, therefore, we need to have a scale which is independent of the what we call properties of the thermometric fluid or the substance. So, for that, of course, we know that alcohol have different TV relations, it is very much required to devise temperature scale. And how can we devise such a temperature scale? For that, what we will do, by using the reversible engine concept from the Carnot theorem 2, that we have seen that the efficiency of a reversible engine or what we call Carnot engine is basically 1 minus QL divided by QH, which is equal to 1 minus TL by TH. And which says that QH by TL is basically a function of TH and TL temperature, both the source and the sink temperature, it is function. So, let us consider the 3 reversible engine, that is reversible engine 1, 2 and 3, which is let us say the reversible engine is absorb what you call Q1 amount of heat and rejects Q2 amount of heat to the sink 2, right, and T1 is greater than T2, and it does the W1 amount of work, right. And let us say that whatever heat is coming from what you call the sink 2 to the sink 2, then that will be absorbed by another reversible engine and it rejects the Q3 amount of heat to the sink T3. That if you look at so far the reversible engine 2 is concerned, this sink is not a sink, this is basically a source for the reversible engine, right, and it is a thermal reservoir. I mean, you call it sinks, or I should call rather it is a thermal reservoir, right. So, it is a basically thermal reservoir, right, thermal. We can act as a source as can a sink depending on the what. Let us say that another engine, that is the third engine, which observes the same amount of Q1 from the source, that is T1, which is at the T1, and it rejects Q3 amount of it to the sink 3 and it produces W3 amount of work. Now, if we look at for the engine 1, we know that Q1, Q2 is a function of T1 and T2, if it is reversible engine, that we have already seen. And similarly, for the engine 2, the Q2 and Q3 ratio is a function of T2 and T3. T2 is the what you call the thermal reservoir 2's temperature, which will be acting as a source for the reversible engine 2, while it will be acting as a sink for the first reversible engine. So, similarly, for the engine 3, we can say that the Q1 by Q3 is basically the function of T1 and T3, right. Now, if you say that like Q1 by Q3 is equal to Q2 by is equal to Q1 by Q2 into Q2 by Q3, it is possible only if that we can say from this that it is basically Q1 by Q3 is a function of T1 T3 and Q1 by Q2 is a function of T1 by T2 and Q2 by Q3 is a function of T2 by T3. So, if you look at this portion, that is if you look at this, if you look at LHS, this is your LHS is the independent of the temperature T1 and it is a LHS is a function of T1 T3 and the LHS is basically independent of temperature T2 only if function as the following form. I mean, that is only possible, right, that if I say that this function, that is f1 this function is basically is equal to g is another function of temperature T1 and is also a ratio of the temperature T1 and T2, and f2 the function f, which is a function of T2 to T3, is basically g T22 divided by g T3. Now, if I say, then only we can say that, because this if it is there, then it will cancel it out, so that we can say that Q1 by Q3 is function of T1 by T3, right, two functions are there. And so, if you look at, if you take a, of course it can be any function, you can say. So, in the more general term, we can write down that equation for a reversible engine is basically QH by QL is equal to the G which is a function of TH and the function of TL, right. And where GT can have several forms, right, you can think of any forms, but by choosing an appropriate function one can define a temperature and which is can be considered as independent of the physical thermometric properties, right. And if you look at Lord Kelvin, he had proposed a simple function. He says that GTH, GT, that is the function, is equal to the temperature. Then he says, and then the selected what you call the relation says that QH by QL will be equal to TH by TL. You may see that people have used a complex function and they have arrived at similar relationship. So, therefore, this is the scale which we call it as basically Kelvin scale, which varies from 0 to the infinity, right. And then expression QH by QL does not really what you call depend on the properties of the thermodynamic fluid, and it can be even though it is a relationship, even though this relationship, it does not really define the thermodynamic scale completely, but it gives a relationship. So, in 1954, the International Conference on Weights and the Measure assigned a value 273.16 to the triple point of water, right. As a result, like you can get one point here, then after that you can find out that magnitude of Kelvin is basically defined as the 1 by 273.16 Kelvin between absolute 0 and triple point of water. Triple point of water like 0.01 degree Celsius, right. So, therefore, he has defined that 1 over 70 and that 0 is considered to be the Kelvin, right, absolute 0. So, by this way one can use the basically the second law of thermodynamics to define a thermodynamic temperature scale which will be independent of the thermometric fluid. So, let us take an example like whether this relationship can be used for solving some other problem. We have talked about a temperature scale, that is of course to to define a scale, Kelvin scale basically defined from that, and then you can use it. But here we will be applying that for solving a problem. Let us say a heat engine operated between thermal reservoir at 500 Kelvin and ambient air at 300 Kelvin is used to drive a refrigerator to produce a temperature of 250 Kelvin by extracting heat of 100 kilowatt from the cold region, right. So, this heat engine is basically giving some work, it is producing some work and that work is being utilized to run the refrigerator. And assuming all the processes to be reversible, and we need to determine the power produced by a heat engine, right, and the ratio of heat energy absorbed by the refrigerant system to the heat energy absorbed by the heat engine, and we will have to also find out the amount of heat rejected to ambient air. So, let us say that there is a source that is T is equal to 500 Kelvin and it is absorbing some amount of heat, that is let us say Q1, and there is a reversible engine which is producing amount of work W dot and it is rejecting certain amount of heat to the sink, that is your sink. Sink is which at what temperature? That is at 300 Kelvin, and of course this sink you can say the same sink, right. And there is a refrigerator, right. I say that RE or I can say this is basically HE, reverse heat engine or the refrigerator, and this region is the cold region, which is at 250 Kelvin. And what it does, it absorbs certain amount of it, let us say this is Q3, and it is rejecting certain amount of heat, that is Q dot 4. Right. What we will have to find out? To find, and this work is being supplied, right. If you look at this work is being supplied. What is that? That is W. That means you can say that this amount of work is being right, this amount of heat being supplied. Now, what is it to be found out? To find, basically we need to find the power produced, W, right, and that is WHE is equal to WRE. RE is the RHE, let me put it, that means reverse heat engine, which is nothing but a refrigerator, right. And how we will find out that? How we will find it out there? We know that coefficient of performance of the refrigerator, what is that? COP of refrigerator, if I say simply RHE, or I can say R is equal to, what is that? What is that? If I say this is TL, this is TL and this is TH, right, this I can say TR, right. Can I say that what will be coefficient of performance of the refrigerator? That is nothing but your TR TL minus TR, yes or no? We have already seen the coefficient of what you call reversible refrigerator, right, or reverse heat engine, whatever you call. So, that is equal to what you call TR is 250, this is 300, this is 250, is equal to what? Is equal to what? That is Q3 divided by W, yes or no? What is Q3 here? What is Q3? Q3 is 100 kilowatt, isn't it? This is your Q3. So, that is 100 divided by W dot. So, W dot would be what? And what is these values? This one 250 divided by the 50, it will be nothing but your 5. This is equal to 5. So, W dot would be what, 20? How much it will be? W dot will be 20 kilowatt. So, I mean we got now the A. So, if you look at this is your A, we got. Now, we need to find out B. What is B? B is the ratio of the heat absorbed by the refrigeration system. How much heat being absorbed? It is 3 divided by the heat absorbed by the heat engine, what it would be? What it is? It is Q dot 1. Yes or no? Right? So, how we will find out that? I can write down this Q3 by W dot, yes or no? Similarly, I can write down Q dot 1 by W1, W dot. So, if you look at Q dot 1, is it we know this one Q dot 1 W? We know or not? We really do not know, but we know this Q dot 3 we know and W dot we know. That is nothing but your what? COP of reverse engine, reverse heat engine or the refrigerator, right? And how I can get this Q1 dot W? How? Basically that is nothing but your Carnot cycle efficiency. What is that? Carnot cycle efficiency, Carnot, I am just writing C, is equal to, by definition is, yes or no, that is equal to 1 minus TL by TH, that will be equal to what? 1 minus 300 divided by 500 will be equal to what? 0.4, can I say? So, therefore, the Q1 will be equal to what? 20, right? Q1 will be equal to 20 divided by 0.4 is equal to 50 kilowatt. Yes or no? Yes or no? So, now we will have to find out basically the what you call, if we know this Q1, then I can substitute over here, that is Q dot by Q dot 3 divided by W is 5 and this is 50 divided by 20, that will be getting what? What will be? This will be 2. Yes or no? This will be 2. So, we need to now find out, that is C Q dot 2, that is the amount of heat rejected. Amount of heat rejected will be Q dot 2 plus Q dot 4. That is the amount of heat rejected to the ambient air, isn't it? Q dot and Q dot 4. So, how we will get this Q dot 2? We know that Q dot 2 divided by Q dot 1 is equal to T L divided by T H. Yes or no? Right. Similarly, we can also find out Q dot 4 divided by Q dot 3 is equal to T 4 is T L divided by T R. From this you can substitute these values, you can get Q dot is basically Q dot 1 T L by T H plus Q dot 3 T L by T R. If you substitute these values, you will get basically because you know that q dot 1 is known. So, T L and T H is known, right. Q dot 3 is known or not? Q dot 3 is given to you 100 kilowatt. So, T L you know, T R you know, all those things you know, you will substitute these values, you will get something 150 kilowatt, right. So, now you know how you can apply what you call this whatever we have derived the relationship, that is basically Q from the what you call thermodynamic temperature scale. We have learned that Q dot or the heat ratio is equal to the temperature ratio whenever the engine is operated between the source temperature and the sink temperature, right. Reversible, it should be reversible, that you should keep in mind. So, now what we will see how we can take this use this second law of thermodynamics for other purposes, and we have we will have to apply this second law of thermodynamics for analysis of engineering problems, and this whatever we have done is basically cyclically operating device, not that all the cycling operating device will be handling, but we will be handling also the what you call various cases. For that, let us consider the Carnot cycle, right, and which will be in this case the heat engine absorb the Q1 amount of heat, right, and it rejects Q2 amount of heat to the sink, which is at temperature T2, and it does the W amount of work because it is a reversible engine, right. So, for Carnot cycle we know that from this the Q1 divided by Q2 is equal to T1 by T2, and from this what will we can write down? We can write down basically here we can say Q1 by T1 is equal to Q2 by T2, and I can take this out, that is nothing but Q1 divided by T1 minus Q2 divided by T2 is equal to 0. This is one relationship which we can derive. So, and of course, this is meant for the reversible engine only, right. So, in this case if you look at, if I take this heat is entering into the heat engine, right, if I take this my system, right, heat is entering, what it would be? It will be positive, and if it is going out it will be negative, right, from the system. If I take this is my system, right. So, then we can write down this expression as Q1 divided by T1 plus Q2 divided by T2 is equal to 0. And this is of course between the two what you call two thermal reservoir. One is of course the source, other is the sink, but there might be several reservoirs, right, one can think of. So, we can write down this expression that what we have derived for the reversible engine, which is operated between two thermal reservoirs. It can be n number of thermal reservoir, we can say that engine can operate. So, therefore, I can write down I is equal to 1 to n, right, and then this I can write down, I mean from here I can write down that Qi by Ti sum of the heat and then heat and temperature ratio is equal to 0. So, let us look at, because all the time we need not to what you call use the heat engine, we will have now considering irreversible heat engine. Irreversible heat engine. Earlier we have considered the reversible heat engine, and again it is taking this irreversible heat engine is taking the heat Q1 from the source which is at temperature T1, and it is rejecting the Q2 dash amount of heat to the sink, and it produces W amount of work. So, for an irreversible engine, we know that according to the Carnot corollary, right, that is the thermal efficiency of the irreversible engine always will be less than the reversible heat engine. So, that means if you look at the irreversible engine efficiency will be what? 1 minus Q2 dash divided by Q1 and less than the 1 minus Q2 divided by Q1, right. And we know for the reversible heat engine, what will be the efficiency? Efficiency will be 1 minus T2 by T1, right, yes or no? From the Carnot, because the reversible engine is your Carnot. This is corresponding to what you call Carnot efficiency, right. Carnot efficiency is not equal to, is equal to 1 minus T2 by T1. So, therefore, I can write down. Can I substitute here in this case? No, I cannot, because that is this one is meant for the irreversible heat engine. So, therefore, I cannot really apply this thing. So, then I can write down here, if you look at, so this is less than that. So, therefore, I can write down here, that is Q2 dash by Q1 is greater than T2 by T1, that is being written here. Okay. So, I can write down that like Q2 dash divided by T2 is greater than Q1 divided by T1. So, using the sign convention, what we have done, we have already discussed, right. In this case, Q1 is basically being absorbed and Q2 dash is given to the sink. That means it is going out of the engine, irreversible engine. So, therefore, I can take this negative and therefore, I can write down that Q1 divided by T1 plus Q2 dash divided by T2 is less than 0. So, this is meant for what? For irreversible engine. And if it is ith number of engines, irreversible engine, I can write down summation of Qi dash I divided by Ti less than 0, right. So, if you combine this equation, that is the reversible engine, which is equal to basically summation of Qi by Ti is equal to 0, that is reversible engine, and irreversible engine will be less than equal to 0. If I just combine this thing, I can write down this expression, that is summation of this heat interaction, basically Qi, ith is the engines, divided by Ti is less than equal to 0, and that is nothing but your Clausius inequality. This is your Clausius inequality. What it states, the Clausius inequality? It states that whenever a system undergoes a cyclic change, however the complex cycle it may be, the algebraic sum of all the heat interaction divided by the respective absolute temperature at which heat interaction take place, consider for the entire cycle is less than equal to 0. That is the Clausius inequality, which just now we have derived from taking very simple concept of the what you call Carnot engine, that is a reversible engine, and we have also considered the irreversible engine and done that. And that is nothing but your mathematically one can write down the Qi divided by Ti sum of over all this thing is less than equal to 0, right. This is basically mathematical expression of the Clausius inequality. And keep in mind that this is basically the second law of thermodynamics, which can be applied not only for the heat engine, also for the refrigeration system, and which must be cyclically operated. That means it is applied for the cyclically, right. And let us consider an example. A reversible heat engine operates between 3 reservoirs, that is at 600 Kelvin, 400 Kelvin and 300 Kelvin. It receives 2500 kilojoule of heat energy from the thermal reservoir at 600 and does the 1000 kilojoule of work. And we need to determine heat interaction with other 2 reservoirs, that is 400 Kelvin and 300 Kelvin, that is the other 2 reservoirs. We need to So, question arises how to go about it. So, let us say that is the heat engine, this is your heat engine basically, I can take this is my best system, I can say, right. Heat being absorbed Q1 to 2500 kilojoule and some heat being rejected to 400 Kelvin, and this heat again rejects Q3 to the 300 Kelvin thermal reservoir, right. And it does the 1000 kilojoule of what you call work. And keep in mind that this is a reversible heat engine, right. So, how we will go about it? We will basically first we will have to look at the first law of thermodynamics, right. So, according to first law, what it says, W is equal to Q1 minus Q2 minus Q3, right. So, if you look at this is given, W is given and Q1 is given and Q2 and Q3 are not given. So, you can't really proceed now, right. You can say, look, this is just energy balance, it is not, like then what you will have to do? You will have to apply now second law of thermodynamics, right. And of course, for this we will have to use the Clausius inequality, that is dq by t over the cycle is equal to the q1 divided by t1, right, minus q2 divided by t2 minus q3 divided by t3, right. Yes or no, is equal to 0, because this is a reversible heat engine. And in this case, this q1 is given and t1, of course t2 is given and t3 is given, but q2 and q3 is are not known. But however, you can get an expression from here, and we have already derived an expression from first law of thermodynamics, that is q2 plus q3 is equal to 1500 kilojoule. So, if we just solve these two equations, we can get that. Let us see, that is we are getting 2500, that is q1 divided by 600 minus q2 divided by 400 minus q3 divided by 300 equal to 0. Why here it is minus? Because heat is going from the engine to the sink. So, therefore, q2 we have taken minus, and so also the q3, the sign convention. And that is your what you call equation 2, we are getting 3q2 plus 4q3 is equal to 5000. And if already we have derived this thing, that is from the first law of thermodynamics, if we just minus here this one. So, what you will cancel? This will cancel it out. So, you will get 7q3 is equal to 500, right. And from that q3 is equal to, from this what will say? You will get q3 is equal to 500 kilojoule, and from the other expression you can get from the equation I mean like from here any one of them, that Q2 is equal to 1000 Kelvin. So, that till now what we have seen that how you can apply the second law of thermodynamics for the cyclic process, right. But not all the processes should be cyclic in nature. There will be some processes which will be non-cyclic in nature, right. Now, question arises how to go about it. If you remember that we have derived the what you call the processes, first law of thermodynamics for the cyclic process first, and then we apply it for the non-cyclic process. What do we do there at that time? Could you recall? How did you do? We have done that already for the first law of thermodynamics. First law of thermodynamics says cyclic integral of the heat will be proportional to cycle integral of the work, and then we say that it is equal to the J is the your Joule's constant, right. And then from that we have derived a expression, that is dE is equal to dQ minus dW, that is the first law of thermodynamics for non-cyclic process, yes or no, right. So, how did we arrive at that? We will be following the similar procedure, right. We will be following the similar procedure to do that. So, I think we will stop over here, but let us recall that what we did. We basically looked at the how to apply the first law of thermodynamics for a cyclic process, right, and we derived the Clausius inequality relationship, right. We say that whenever a what you call reversible engine, whenever the heat engine will be interacting with the what you call system, and its whenever it will be interacting with the thermal reservoirs, right, source and sink, however the complex cycle it may be, the sum of the heat interaction and the respective thermal reservoir ratio will be equal to less than equal to 0, right. So, that is the thing what we have seen. So, if you look at, we have seen whenever a system undergoes a cyclic change, however the complex cycle may be, the algebraic sum of all heat interaction divided by the respective absolute temperature at which heat interaction take place, consider for the entire cycle is less than equal to 0. That is the Clausius inequality. And before that, of course, we have seen that how one can devise the thermodynamic temperature scale by using the second law of thermodynamics. So, in the next lecture, what we will be discussing basically how we will apply the second law of thermodynamics for the non-cyclic process. Thank you very much.